All right, so this is section 5.3. So we're not doing this in the regular Math 120. This is about the area of a triangle, so we'll talk about the traditional formula for the area of a triangle, and then we'll come up with a couple formulas for the area of a triangle um, that can be used in slightly different contexts, like if you have different kinds of information about your triangle. This is, again, we're doing this in Math 92. This is probably one of the least important topics in the Trig class, so I don't think it's even worth it to do it in Math 120. So one thing to note, this will not show up on any exams in Math 120. Okay, so this section is about the area of a triangle. So let's start with the traditional way of calculating the area of a triangle. So let me draw a triangle right here. Let's call this side here B. Traditionally, the way you would calculate it is you drop this perpendicular down here, and if you call this this length here H, the area is 1/2, so area is equal to 1/2 base times height, right? B for base, H for height. Okay, the reason this is true is because if you think about this right triangle here on the right, I can duplicate it on the other side right here, like that. And these two triangles, this one and this one, they're congruent, so they're exactly the same triangles, right? Because, for example, they both have this right angle here, right? They both share this side there. And they share these two heights there, all right? So these two triangles are exactly the same. And so what we end up with, well, because we have a right angle here and a right angle here, is we have a rectangle. So this whole business here, let me kind of shade that in a different color. This whole guy here is a rectangle, and so its area would be the base of this rectangle. So let me call this guy right here little b1, and so it's the area of the rectangle is equal to little b1 times h, right? So just from the traditional formula for the area of a rectangle. Okay, and because these two triangles are congruent, the portion of the triangle we care about, right, the area of that has to be the half of the area of this rectangle, right? Because the other half is exactly the same size, right? So area of the triangle, the portion, let me write it like this, portion we care about is 1/2 B1H. All right, so the portion we care about, meaning that guy right there. Okay, in exactly the same way, we can do the same thing on the other side. We have this right triangle here. We can create a rectangle right there, right? These two triangles are congruent. So they're exactly the same. So in particular, they have the same area. And the area of the rectangle is, if I call this guy B2, the area of this rectangle is B2 times H, right? But that's equal to, so let me write it like this. So area of the portion we care about and that would be this guy right here, is half of that, right? Because again, this right triangle there and this right triangle there are exactly the same size. So they have to be, each have to be half the size of the full rectangle. All right. Okay, so altogether, the triangle that we care about consists of these two smaller right triangles. One of them has area 1/2 B2H. The other has area 1/2 B1H. So the area, so total area of triangle is 1/2 B2H plus 1/2 B1H. And if I just pull out the 1/2 H, I get B2 plus B1. But if I look at this, of course, B2 plus B1 is the full length B, right? So this guy is equal to B, and so I get 1/2 base times height. Okay, so this is where the traditional formula for an area of a triangle comes from. Okay, so what we're going to do is get a couple different formulas that can be used in different contexts. So this one is very useful if you know a base and a height, right? So if I know the base and I know the height, then obviously I can just plug them into the formula. But perhaps in a lot of circumstances, you might not have especially the height, right? Because the height is not really a natural quantity when you're talking about a triangle, right? Natural quantities are kind of the angles, this side, or this side, right? So oftentimes you're not going to have that height. So either you'd have to figure out the height, or you can use one of the formulas that we're going to write down right now. All right. Okay. So the first formula just comes directly from thinking about the angles. So let me draw a triangle like, so I guess I used B there. So let me use beta here, B here, alpha here, gamma here. So we're using the same notation as in the law of sines and cosines section. All right. What I'm going to do is I'm going to drop this perpendicular down here, right? And I know the area of this triangle is B times the height of that perpendicular, right? Just 1/2 B times the height of that perpendicular, just from the formula that we just talked about, right? So let me call the height of this perpendicular. I guess I'm using lower cases here, so I'll use lowercase h. All right, so actually h is really bad because h kind of makes you feel like hypotenuse, right? So let me call it something different. Let me call it y. Okay, so area is equal to 1/2 base B, right, times the height y. Okay, but again, like we said, in a lot of contexts, you don't know the y. So let's rewrite this. This is 1/2 B, and what is y? Well, this is a trig class, so we want to look at this angle alpha. Sine of alpha is equal to opposite y over hypotenuse c, right? Because again, we've done this many times. We've dropped this perpendicular, so we have a right triangle right there, all right? And so y is equal to c sine of alpha, right? And so this y up here in the area formula can become c sine alpha, all right? And that's it. This gives me an alternate formula for the area of a triangle, but this formula here involves this angle, this base right here, or this length right here, and this length right here, C. All right. So if you know essentially the side angle side of a triangle, you can write out its area, at least a formula for its area, in a very straightforward way. Okay. I'll leave it to you to do the same thing for the situation where you need to figure out. So this one, right? I've specifically written it out for C, alpha, and B. So a good exercise for you is to do it for B, gamma, and A. Right? You can have a corresponding formula. You'd have to drop the perpendicular as well, and then also for beta, C, and A. Right? So you find formula in terms for area in terms of C beta A, and also a second formula for B gamma A. All right. Using the same ideas, right? By dropping the perpendicular and so on. Good exercise because that'll help you kind of understand the way we did it here. Okay, so ultimately, you would have three formulas for finding the area. So this method gives you three formulas for finding the area of a triangle, right? One for each of the angle and two sides. So this could be useful in some contexts. And of course, in the homework, you'll find some problems where they ask you to do it this way. However, what if you don't have the angles, right? So in our first method, the problem was that, what if we don't have the h? In the second method, what if you don't have the angle, right? In a lot of situations, when you're given a triangle, all you're given are the lengths, right? Maybe this length, and that length, right? So in that situation, it's not so easy to use the two methods that we've just talked about. So the question is there a formula that allows me to write down the area of a triangle just from knowing B, A, and C, right? And luckily enough, there is. And actually, the nice thing is, in terms of kind of the flow of this video, it actually comes directly from what we just talked about. So what we just got was that the area was 1/2 BC sine of alpha, right? We don't like the sine of alpha, right? Like we said, perhaps we only have A, B, and C, the lengths of our triangle. So how can we get rid of this sine of alpha? Well, one thing we know is that if we square both sides, we can get a sine squared of alpha there, right? And we know that sine squared of alpha can be converted to cosine of alpha, cosine squared of alpha, right? Now that doesn't sound like it might be very helpful, but we also know that the law of cosines involves a cosine of an angle, and everything else in the law of cosines is a length. So if we convert that cosine into lengths, then all will have our lengths, right? So let's do exactly that. So this tells me the area squared is 1/4 b squared c squared sine squared alpha, right? Okay, and let's rewrite that as 1/4 b squared c squared 1 minus cosine squared alpha. All right. Okay, and again, this looks terrible, right? It looks even worse than our initial formula. But again, our strategy is that we know the cosine squared can be converted into something nicer. So this is 1/4 b squared c squared. Actually, let me distribute that in just to so I can release that from the parentheses. 1/4 b squared c squared cosine squared alpha, right? And the law of cosines tells me, so I have a picture up here, right? Here's alpha. The law of cosines that involves alpha tells me, oh no. All right, sorry about that. The law of cosines that involves alpha tells me that a squared equals the other two, b squared plus c squared, minus the other two, 2 times bc, cosine of alpha. All right. Okay, so we actually have b, c, cos alpha, and here is a b, c, and a cos alpha, whole thing squared, of course, right? So what I'm going to do is I'm going to actually throw everything except the b, c, cosine alpha to the other side, okay? So, I guess I should write this is law of cosines, right? So I'm going to throw everything else to the other side. So I'm going to end up with a squared minus b squared minus c squared equals minus 2 bc cos alpha, right? I'm going to divide by minus 2 on both sides. So I end up with minus a squared minus b squared minus c squared over 2 equals BC cos alpha, right? I'm going to square both sides because, again, my goal here is to match this guy with that guy there, right? And that guy up there has squares, so I want to see squares. So I'm going to square both sides. Now I'm going to end up with b squared c squared cosine squared alpha is equal to once I square it, the minus goes away, right? So a squared minus b squared minus c squared over 4, and then this guy up here needs to be squared. All right, so I'm squaring the left-hand side. Okay, now I can substitute this, this expression for my b squared c squared expression right there. All right, so to continue here, what I get is my area squared is equal to 1/4 b squared c squared minus 1/4, and then this stuff over here, a squared minus b squared minus c squared, whole thing squared, 1/4, right? And let's rewrite that as 1/4 b squared c squared minus 1/16, a squared minus b squared minus c squared, whole thing squared. Okay, so that's my area squared. And so, of course, that means my area is square root of that. And again, normally when I square root both sides of an equation, I need to pop out a plus or minus. But we're talking area here, like the physical area of a triangle, which has to be positive, right? Physical areas have to be positive. So I know I don't need the negative sign. So 1/4 b squared c squared minus 1/16. Actually, I should probably pull out this 1/4, right? So let's pull that out as 1/2. Sorry, let me not skip steps like this. Let me rewrite this as 1/4 like this: b squared c squared minus 1/4 a squared minus b squared minus c squared, whole thing squared, right? And then I'm going to square root both sides. Area is equal to, when I square root both sides, the square root of 1/4 becomes just 1/2. And then square root like this. Just, it makes it look a little nicer. Okay. All right. And that's it, right? So our goal is satisfied. We wanted the area, and we wanted it in terms of only the side lengths, right? So on the right-hand side, we can see side length, side length, side length, side length, side length, right? No angles, no dropping perpendiculars and trying to figure out the lengths of those, right? Essentially, if I give you a triangle and I tell you this length is 10, this one is 7, and this one is 8, then you can figure out the area of that triangle just from those 3 bits of information using this formula here. Okay, so pretty nice, right? You didn't need the angle, you didn't need to drop a perpendicular. So here's our formula. And again, we based our formula on our area formula up here that we got earlier, right? This one right there. Yeah, this one that we got earlier, right? And of course, you can figure out 2 other formulas for the area, basing it on the other 2 formulas up here, right? That you hopefully calculated as well. Okay. Now, if you look in the book, they have a formula that's slightly different for the area, because what they did was they took this formula here and they did some manipulations to it to make it a little nicer in a way, a little more elegant. But ultimately, if all you need is to calculate the area, the way we did this here works just as fine. All right. The one the book found, or the one the book does, they give it a name, or there is a name for it. It's called Heron's formula. It's not very important at all. Again, for us, for this class, just know that you can find a formula for the area of a triangle using just its lengths. And this formula here is good enough, right? We don't need really a fancy formula for it because we're not really going to be doing too much with it. Actually, we're not going to be doing anything with it further on in our class. But again, I think it's a good idea to do this calculation using the other points of views, or using the other two formulas for the area in terms of the angle and two sides. All right. All right. So just a kind of small, interesting section. Next time we will revisit solving sine and cosine equations, except in the context of having quadratic equations involving sines and cosines. So for that, we'll focus on reviewing how to factor quadratic equations, and then we'll put it together to deal with situations where you actually have sines and cosines in for your variable x.